Yeah.
So let's start. Hello everyone. Welcome to the first talk of the fall semester. Uh, we are going to start this semester with a foundational course on metric space and topology. The first talk will be given by Mayank. He's a math first year student. So over to you, Mayank.
Okay, so hello everyone. This talk is mostly going to be about metric spaces and some motivation for why do we need a topology. So I guess everyone over here is familiar with analysis on real numbers, like real analysis one course. So I'm going to start with that. So uh, so for doing real analysis, uh, we need a notion of a distance. So i- in the case of real numbers, the distance between two numbers is given by mod of x minus y. And this distance serves as the foundation for the whole of analysis on real line. What we want to do is we want to generalize this notion of a distance to arbitrary spaces. Those spaces are called metric spaces. So I will define this for you. I guess everyone over here is familiar with metric spaces. So metric spaces. So metric space is a set X together with a distance on it, which is a function from uh, which is a function from x cross x to positive reals, which satisfies certain conditions. Uh, am I audible?
Yes, you are audible.
Okay, okay, fine. So a metric space is a set together with the notion of a distance, which is a function from x cross x to positive reals, which satisfy these following conditions. So we want the distance between x and y to be same as the distance between y and x. If the distance between 2 points x and y is 0, those points should be the same. and the distance should satisfy the familiar triangle inequality. So a set together with the function satisfying these properties, a set together with a distance satisfying these properties is called a metric space. I hope everyone is familiar with this notion. So let's see some examples. So the usual real numbers together with this function, I'm sorry, together with this function d, which is given by distance between x and y is x minus y. This is a metric on real numbers. So real numbers together with this function is called a metric space. Similarly, we can define a metric on Rn, which is given by the usual, the familiar Euclidean norm, the Euclidean distance between these 2 points. This is a metric on Rn. Okay.
Can you scroll up a bit? I just want to see the first part.
Oh, acha.
Okay.
Is this okay?
Thank you. Thank you.
Uh, so these are the usual distances that we are familiar with. I want to give one more example. Is it okay if I scroll up now?
Okay.
So I want to give one important example, which is the distance on linear spaces or vector spaces. Non-linear spaces. So in R2, any point x comma y in R2, the distance of this point x comma y from 0, this is called a norm on R2, which satisfies certain properties. So this distance is called R2. I will represent it like this, which is equal to x square plus y square square root. So this thing is the distance of this point from the 0, 0, 0 vector. This function on R2 satisfies certain properties, which are, this is always positive, and if for certain y this is 0, then this y should be 0. And if I scale this vector by some scalar alpha, then the length gets scaled by the same factor. And this should also satisfy the familiar triangle inequality. So this is a very natural notion of distance between x comma y and 0 comma 0. We want to extend this notion to linear spaces or vector spaces. So for arbitrary vector spaces, say V is a vector space, a norm on V is a map from V to positive reals, such that if the norm is 0, then the vector should be 0. Positivity of the norm is covered over here. If I scale the vector by some scalar alpha, the effect should be same as scaling the norm of the original vector by alpha, by mod alpha, I'm sorry. And it should satisfy the triangle inequality. So a function like this is called a norm on the vector space. And if a vector space is endowed with such a function, we call it a non-linear space or a non-vector space. Is a vector space V with a norm on it. So this notion of norm also induces a metric on the vector space, which is given as follows. So if this is a metric, this is a norm on V, then if we define a map like this, where x and y are elements from the vector space, then we define distance between x and y to be norm of x minus y. And it is an exercise for you, all of you, to check that this is actually a metric on V. Okay. So these are some examples of metric spaces. So we want to define
Excuse me,
open.
I want to say that I want to say this to the instructor that I joined a bit late. So can you just like give a quick summary of what you did right now?
Okay, fine. So what I did is, so we have, so do you know metric spaces?
Somewhat.
Okay, so metric space is just a set together with a distance upon it, which like takes two elements from the set and gives out the distance between them, which should satisfy the familiar properties like distance between x and y should be the same as distance between y and x. If the distance between x and y is 0, then the points must be the same, and it should satisfy the familiar triangle inequality. So this is a metric space. Then I gave few examples of metric spaces. One of the familiar example is the real line together with this distance between 2 points, which is given by mod of x minus y. And on Rn, we also have this usual Euclidean distance between 2 points. So I guess you should check that these two functions satisfy these three properties. So these are familiar examples of metric spaces. And then I define non-linear spaces. So norm on a vector space V is a map which takes elements of V and which satisfies the following property. Like if the norm is 0, then the vector must be 0. If I scale the vector and take the norm of it, it should be same as taking the norm of x and then scaling it by mod of whatever the scalar is. And it should satisfy the familiar triangle inequality. And then I gave as an exercise that this map px comma y, which is defined as norm of x minus y, this gives a metric on V. This is what I have covered till now. Is it okay for you?
Yes, sir. Thank you.
Okay. So going further, I want to define open sets, and we want to see how useful open sets are. In some sense, we can do whole lot of analysis just using open sets. So we want to see that. So I want to define open sets on a metric space. Okay. For that, I need to define notion of open ball in a metric space. I will define open balls. So to give some motivation, if this is R2 and in open ball with center 0, 0 of radius 1 is the set of points x, y in R2 which are at a distance of strictly less than 1 from 0, 0. So set of all these points is a ball centered around 0 of radius 1. So we can define this for arbitrary points. So open balls with center x, which is some element of a vector space, and radius r, which is a positive number, is defined as, by the way, this is the notation for ball of radius r with center x. This is defined as set of all the points, set of all points y in x, such that whose distance from x is strictly less than r. So balls in R2 looks like this. So to give some more examples of how open balls look like. So these are open balls in R2. This. So I will define a norm on R2 which should give a distance upon it, which is norm x, y is mod x plus mod y. I think it's clear that this is a norm on R2, and the distance that this norms induces on R2 is the following. Sorry. X2 minus Y2. This is the distance induced by this norm on R2. So let's see how open balls in R2 looks like with this distance. So ball with center 0, 0 of radius 1 is exactly the set of points y in R2 such that 0 minus y1 plus 0 minus y2 is strictly less than 1. So if you graph this thing, it should look like this. And this dotted line means that these lines themselves are not a part of this set. Is it clear to everyone that this set looks like this? If it's is it clear to everyone?
Can you explain one more time?
Fine. So uh, in R2, I defined a norm. I think you should check this. This is an exercise. and this norm gave a distance on R2, which looks like this. So
Excuse me, sir. I
let
don't
me,
understand what is the exercise you're referring to. Like, what do we need to prove here?
okay, so you need to show that this function, which takes x comma y as an input and returns mod x plus mod y, is actually a norm on R2. This is the exercise that you want to do, that you should do. And I showed, I gave you another exercise that a norm induces a metric on the set. So I defined, okay, I will do this once more.
Like, norm is a distance function defined in a vector space. Is it correct?
Norm is just a map from V. I will show you. I just gave an intuition on what a norm should be. This is in some sense a distance from zero to that vector, but we are abstracting out the definition. Okay. So a norm takes as inputs elements from V and returns positive real numbers, and it satisfies these three properties. A function like this is called a norm on R2, a norm on V. Okay. And I want you all to check that this map that I defined, this takes R2 to real numbers. This is a map from R2 to R. So I want you all to check that this is actually a norm on R2. Is it okay? Or I should do it for you once?
It would be like helpful if you can do it just once. Like, for example.
Okay, fine. I will check those three properties for you. Okay.
Yeah, thank you so much.
So this is defined as mod x plus mod y. Okay. So first we need to check that. So what are the properties of norm? If the norm is zero, then the vector should be zero itself. So if x comma y, if this is zero, what does this mean? This means that mod x less mod y is equal to zero. This implies that x and y both are zero, which means x comma y itself is zero vector. So property one is verified. Property two is if I scale the vector, the scalar should come out. Let's check that. So norm alpha x comma y. So this scaling is defined as alpha x comma alpha y. It is like this. And we define this norm to be mod alpha x plus mod alpha y. This is equal to mod alpha mod x plus mod alpha mod y. This is equal to mod alpha mod x plus mod y. This is equal to mod alpha norm of x comma y. So this was the second property of the norms. Okay.
So, like, I had this question that how do you define the norm of a field element? Like, you have put alpha in norm instead of modulo. So, like, I was confused there.
Oh, really sorry. So I am taking vector spaces over R over here. R or C. So this mod by mod alpha, I mean the absolute value of alpha. Okay. I'm really sorry for that. Oh, is it
Okay.
clear? Huh.
Yes, sir.
So this is the usual mod alpha that we take in real numbers, okay, or in complex, whatever. So the second property is also verified. Now we want to check the property 3, which is the triangle inequality. So if I take two vectors, x comma y and x tilde y tilde, then this is equal to norm x plus x tilde comma y plus y tilde. This is defined to be equal to mod x plus x tilde plus mod y plus y tilde. And by the triangle inequality of mod that we learned in real analysis 1, this is less than equal to mod x uh, plus mod x tilde plus mod y tilde, which is equal to mod x plus mod y plus mod x tilde plus mod y tilde. And this is the definition of norm x comma y, and this was norm x tilde y tilde. So we showed that sum norm of sums is less than equal to sum of norms. This was the triangle inequality that we needed to verify. So is it okay that this map is actually a norm on R2? Is it okay?
I had a doubt in the mid like my doubt was that we couldn't really abstract the thing out. Like we have put mod alpha, but like what is mod alpha exactly?
So since we are taking vector spaces over R, so the scalars come from real number or complex numbers. So here, okay. So
like, in that case, how do we abstract it instead of like
what?
working on only real and complex?
So for real analysis, we are concerned mostly with vector spaces over R and complex numbers, because these properties are very important to do analysis. So we want them basically. So analysis is mostly concerned with vector spaces over reals and complex numbers. General things are those are concerned with like linear algebra and those things. So for now, we are working only with vector spaces over R and complex numbers. In that case, this should be fine, right?
Yes, yes.
Okay, fine. So I think we can move forward. So this is actually a norm on R2, and the distance induced by this norm on R2 is given by norm x tilde minus y. So the ball centered at 0, 0 of radius 1, this is the set of all points in R2 such that uh, 0, 0 minus y1, y2 strictly less than 1. So these are all the points y in R2, so that mod y1 plus mod y2 is strictly less than 1. And the set of all these points should look like this. I hope this is clear now. Is it okay for everyone? Okay. So the shape of the ball, it depends upon the norm that we are using. So these are some examples of open balls. Now I want to define open sets. So if X is a metric space and U is a subset of X, It is called open if for every point in that set I can find some radius such that the ball of that radius fits inside U, such that lies inside U. So if this is U and X is any point, for every point of U, I should be able to find a radius so that the ball fits completely inside U. So these kinds of set are called open sets in a metric space X. That is the definition clear to everyone? Okay, fine. So
Sir,
yes.
if one ball is fine like that, then we call it open set.
What is the question? I didn't got.
I- If there exists one ball,
Yes, yes.
okay,
If for some point, if for all the points I can find at least one ball such that it fits completely inside U, then it is called open.
okay, sir.
Okay. So uh, I want to show some properties of open sets. Property 1. If I have a collection of open sets in X, U alpha, these are open sets in X, then their union is also a open set. Union of U alpha. Okay, this notation is a bit weird, but okay. This is also open in X.
In the last
So
example, was X a metric space or was was X an open set or was U an open set?
U. A subset of X is called open
Okay,
if for every point of that set I can find a ball which fits completely inside U. Okay.
okay, thank you.
So ex- exactly. So that implies that X itself is an open set. So for to verify this property, what do we need to check? Say X is a point of the union of these open sets. Then this X is an element of some U alpha. But since U alphas are open, then by the definition of open sets, we know that there is some ball which fits completely inside U alpha. But since U alpha is a subset of the union, this ball also fits inside the union. Therefore, for every point of the union, I am able to find a ball which fits completely inside this set. Therefore, the union is an open set. Is this clear to everyone? Okay, fine. So let's move towards second property. If I have two open sets, U1 and U2, open, then their intersection is also open. I want to show this. So since these open sets, for every element of this open set, I can find a ball which fits completely inside this set U1. Therefore, okay, so let me write that. So for every x in U1, there exists a radius such that the ball of that radius fits completely inside U1. Therefore, this U1 must be the union of all these balls. Let me write it like this. This radius depends upon x in U1. So is this clear to everyone how this equality follows?
Yes, sir.
Okay. So every open set can be written as union of open balls. This is what we saw over here. So therefore, U2 can similarly be written like this as union of open balls. Therefore, U1 intersection U2. So U1 looks like this. Y U2. So by the distributivity laws of union and intersections, this becomes B x comma Rx intersection B y comma Ry union over x in U1 and y in U2. So if I show that union of intersection of two open balls is open, then from the property 1 we can say that this uh, this intersection is also open, because intersection of two open balls is open, and if we take union of open sets we get another open set. So we will show that. So
How
what I
do you
want to say
say
is,
that the intersection of two open balls is also open?
so we are going to prove that. So I'm saying it is enough to show that intersection of two open balls is open to show the property number 2. Okay. So it's enough to show in property 2 for open balls. Okay. So if I have two open balls, the shapes might look different, but I'm just drawing it like this. Um, so this is the center, and the radius is R2, R1. So I want to show that this intersection is also open. So by the definition of open sets, I need to show that for every Z which is inside, I will call this B1 and B2. Uh, B2. So I need to show that for every Z which is common to B1 and B2, there exists a ball of some radius which lies inside this intersection. So let's take, so basically I want to minimize in some sense these distances from the boundaries, and in some sense I want to find the minimum of the distance of Z from these boundaries so that the ball fits completely inside this region. Okay, so we will use triangle inequality for that. So define R to be the minimum of R1 minus distance between x and z, comma, R2 minus distance between uh, y comma z, this distance. Let's give them some names, say alpha 1 and alpha 2. So this is the minimum R1 minus alpha 1 comma R2 minus alpha 2. So what I claim is that this radius suffices. So what I mean by that is the ball with center z of radius r, this lies completely inside B1 intersection B2. So let's check that.
Can you say what was R1 and R2 once again?
So R1 is the radius of the first ball. So this distance is R1, and this ball has the radius R2. Okay. And alpha 1 is the distance between x and z. X is the center of the first ball. And alpha 2 is the radius between y and z. Y is the center of the second ball. So I defined R as minimum of R1 minus alpha 1 and R2 minus alpha 2. These are positive. Okay. So we need to show that uh, this ball with the radius that I gave actually fits inside the intersection. Okay. So what does this mean? So for if I take any point x in this ball, then the distance between this, oh sorry, I should not take x. Let's take what, say theta. If I take any point theta in this ball, then the distance between x and theta must be less than r1, and the distance between y and theta must be less than r2 for this ball to be contained in the intersection. This is what we have to show. Okay. So by triangle inequality, we know that distance between distance between uh, let's draw some pictures over here. We draw it over here only. So theta is some point over here. Uh, so we want to show that the distance of theta from x is less than r1, and distance of theta from y is strictly less than r2. So distance between x and theta is less than equal to the distance between x and z plus distance between z and theta. So this is the triangle inequality that metric metric function follows. And okay, so this theta has distance, since theta lies inside this ball z comma r, therefore the distance between z and theta is strictly less than r. So distance between x and theta less than equal to distance between x and z. Sorry. Mm, this is less than distance between x and z plus r. I think I did something wrong. Distance between, okay, let's do it some other way. So what do we want? We want to show that distance between x and theta is less than r1. So
I think you are doing right.
oh, is that the case?
You at the next step you will do r is less than r1 minus d of xs. Then d of xs will cancel out, and you will get the result.
Oh, acha, acha. I thought, okay. So, uh, so should I do it or is it okay for you? Like it will just follow
It's
from
okay. It's
triangle
okay.
inequality. Yeah. Like some manipulation and you will get that. Okay. So, so, th- so by using triangle inequality, you can basically show this thing, and this shows that the ball of this radius r is actually this lies completely inside the intersection. Okay. So this shows that intersection of two open balls is open. Intersection of open balls is open, and from this thing we can say that, and by using property 1 we know that union of open sets is open, so we can say that u1 intersection u2 is also an open set by using property 1. Therefore intersection of open sets is also open. This follows from property 1 and this fact. Okay. So these are two important properties that open sets follow.
It should be intersection of finite open set. Finite
So
element. Like, we did it for
exactly.
two.
So since intersection of two open sets is open, so by induction it follows that it should be true for finitely many open sets. So therefore it is also true for finitely many open sets. Finitely many open sets. Like this follows from u1 intersection u2 intersection say un. Then all of these u1, u2 up to un, these are open. Therefore, u1 intersection u2 is also open. And then we will go one more step and continuing like this, we will get that the whole of the intersection is open. So this follows from induction.
I think instead of using induction, if we took one point here, then for every ui we would get some ri depending on x.
Okay.
Then we take the minimum of those ri's, and then it can follow without induction that bx comma r is a subset of all this intersection.
Yeah, you're right. That also works. That will also work. Sure. Okay. So you can do it the other way, or you can do it the way that you just told. Take minimum of radii that you get for all the open sets u1, u2 up till un. That will also work. Okay. So for those of you who didn't got this is an exercise for you. Okay. So arbitrary union of open sets is open and intersection of open sets is also open. This is what we have shown. And so one technical point is the empty union of open balls, which is the empty set, it should also be open, is also open. Basically, what does this means is the condition for open set is vacuously true because there is no point in the empty set to verify those properties. So empty set is also open, and clearly X itself is open. You take any point, then you take radius, you take any radius, it will definitely be contained inside X. So for every point, you can find a ball which is contained in it. So X itself is open. Okay. So the way that you prove that intersection of two open balls is open, using similar ideas, basically the triangle inequality, you can also show that. So another homework for you guys, another easy exercise for you all is that uh, open balls are also open. Open balls are also open. This also follows from the triangle inequality of the metric. Okay. So we will now try to motivate.
I just want, sorry, I just want to ask something. If
Uh,
if there are two open balls, U1 and U2, and they are tangent to each other, means there is only one point which is common in both. Like,
okay,
so in that case, how we will prove that intersection of these two open balls is also union?
so open balls, they don't actually contain the boundary. So what you were saying is they're tangent. What were you saying? Can you repeat?
Sorry, I forgot that point. I'm sorry.
Yeah. So basically, you can't have a single point, uh, which
Yeah,
is
I'm just on the boundary.
yeah.
Sorry.
Like you take the radius. Say these are two balls, and the point which is common to both the open sets. So for that, you can find another open ball of some radius, and for the other open set, you can find another radius R2. Take the minimum of these. So this minimum of these two radii, say call that R, then B x comma R lies in both of these sets. Okay, so that's how you do it. Okay.
Sir, the technicality you mentioned where that empty set and X are both open.
Yeah.
Okay.
X open is not that technical, but uh, empty set is open. That is somewhat technical. It is vacuously true.
Okay.
Okay. So now we will try to give some examples which will show you the importance of open sets. So let's start with the most important thing that we do in real analysis, which is convergence of sequences. Okay. Convergence of sequences in a metric space. So X is a metric space, and if I have a sequence sum which is called Xn, then we say that Xn converges to some point X if for every epsilon positive there exists a natural number n such that the distance between Xn and X is less than epsilon for every n greater than or equal to n. So this is the usual definition of convergence that you learned in real analysis 1. What I will show you that this definition can also be mimicked just by using open sets. So
Excuse me, sir. Point X, like the point where it is converging, it has to be in the metric space.
yeah, it should be. Where else the point can be? Like, we don't know what other things are there outside X. A sequence may not be convergent.
Okay, right. Actually, because the definition of distance doesn't make sense outside of
Exactly.
X. Yeah.
True. Yeah. So if a sequence, if there exists a point X such that these properties hold, then we say that the sequence converges to X. Otherwise, we say it is not convergent. Okay. So my claim is that this definition of convergence, this can be mimicked just by using open sets in this metric space. Okay. So my claim is that a sequence converges to X if and only if for every open set U which contains X such that X belongs to U, I can find a natural number N such that all the points of this sequence belong to U after this natural number. So what this means is the notion of convergence can be captured just by using open sets. So we don't need this, we don't actually need this epsilons and deltas. We can just capture this convergence, notion of convergence just by using open sets. So I will try to prove it. Okay. So if xn converges to x, so this is the first direction that we are proving, then I need to show that, then I need to show the second part. So let U be an open set containing X. But by the definition of open sets, uh, okay, there exists a ball of some radius, let's call that epsilon. So by the definition of open sets, there exists some epsilon positive such that the ball centered at X with radius epsilon lies completely inside U. So by the definition of convergence, for this particular epsilon positive, I should be able to find a natural number. So there exists a natural number such that xn has distance less than epsilon from x for every n greater than or equal to n. What does that means? This implies that xn belongs to this ball of radius epsilon centered at x for every n greater than or equal to this capital N. But this sits completely inside U. Therefore, xn's all belong to U for all n greater than or equal to capital N. So I hope this is clear. Is it okay for everyone? Yes. Okay, so I will prove the second direction. So for the second direction, we will use the homework that I gave you, that open balls are open. Open balls are open. So we need to show that given an epsilon positive, I need to find a natural number such that all the elements of the sequence lies at a distance less than epsilon from x. So construct this ball around X with center epsilon, and this is an open set. But by the hypothesis of this thing is, if for every open set, I can find a natural number such that all the points lie inside this open set after a certain point. So there exists a natural number n such that xn belongs to b x comma epsilon for all n greater than or equal to n, which means xn has a distance less than epsilon from x for all n greater than or equal to n. Therefore, we showed this equivalence. So the point was to just show you all that convergence can be captured just by using open sets. That is the main point that we are trying to show. We can similarly show some other very nice properties that we want. So one of the most important properties that we uh, study in real analysis is continuity of functions. Continuity of functions. So the notion of continuity also, this can also be captured just by using open sets. So the usual definition of continuity is that, so I have two metric spaces, say x comma d1 and y comma d2, and I have a function f between them. It is called continuous if for every x inside x, and given any epsilon positive, I can find a delta positive such that if the distance between uh, x and y is less than delta, then the distance between f of, oh, I'm sorry, then the distance between f of x and f of y, this should be less than epsilon. So this is the usual definition of continuity of a function. So my claim is that,
By any chance, is this thing called like homeomorphism or something like that?
yeah. So between two metric spaces, a continuous mapping which is bijective and whose inverse is also continuous, in that case, it is called a homeomorphism. So we will get to those things in the next lecture. Okay. So my claim is the notion of continuity can also be captured just by using the open sets. So f is continuous if and only if for every open set inside Y, f inverse of u is open in X. So f inverse of u, it is the set of all points inside X whose image lies inside U. Okay. So the notion of continuity, this can also be captured just by using open sets. So I will just prove one of the sides, and you also try to prove the other side. I don't think this is too difficult. So so I will prove the side. I will prove this side. So for every open set U in Y, f inverse of U is open in X. So we need to show that. So we need to show this definition. Now, so take any for every x in X, and given any epsilon positive, I need to show existence of a delta which satisfy this definition. So take the ball with center f of x and radius epsilon. I gave you all as a homework that open balls are open. So this is an open set. Therefore, the pre-image of this set, this is open in X, and clearly X is contained in this set. So this set is open by the hypothesis, and by the definition of open sets, there exists some, I will call it delta positive, such that the ball centered at X of radius delta fits completely inside this pre-image. So this follows from the definition of open sets. Okay. Therefore, for every y such that whose distance from x is less than delta, this implies that y belongs to b x comma delta. Therefore, it also belongs to this set, which means f of x belongs to the ball with radius epsilon centered at f of x. That, oh, sorry, this is y. That is distance between f of x and f of y is less than epsilon. For any point y which has a distance less than delta from x. So the other side, it is a homework for you guys. So this shows that the notion of continuity, which is very important, this notion can also be this also can be captured just by using the open sets. So indeed, open sets are useful, and I will give you one more example for that. Okay. So dense sets. So given a metric space X, a subset A of X is called dense in X if for every element of X there exists a sequence in A such that the sequence converges to that point. So is the definition clear to everyone? So in essence, what denseness means that for every point of the metric space, I can find a point of A which is arbitrarily close to that point. So to give some examples, rationals is a subset of R with the usual Euclidean distance. This set of rational numbers is dense inside R because for if so if I pick any number R, if I pick any number X from R, if it is rational, then I take then I take the constant sequence x. This converges to x. And if it is irrational, then I can use the uh, what it is. Then I can use the decimal expansion of the irrational number to construct a sequence which is contained in rationals, which converges to that number. For example, if I take pi, which is 3.14, so on. So I will consider this sequence 3.1, 3.14, 3.141, and so on. So this sequence will converge to pi. And all of these are rationals. So basically, this means that I can find a element in rationals which is arbitrarily close to any given point in real numbers. Huh. Okay. Oh, acha. So x, and after that, okay, okay, yeah, true. I think we need to add the integer part also, right? Or oh, sorry, yeah. This is like sorry. I confused this with the fractional part of x. Sorry, So this sequence will go to x. So this is the explicit sequence constructed by Bikram for any real number x, and this is a rational number. So rationals are dense in R. So what this means is, given, so this can be phrased in other language also, that given any epsilon positive and a number and a real number, I can find a rational number whose distance from the given number is less than epsilon. So this follows from the sequence that converges to x. Okay. So my claim is the notion of dense sets can also be my claim is this notion of dense sets, this can also be captured just by using the open sets of the metric space. So A, which is a subset of X, is dense if and only if for every open set U in X, U intersection A is non-empty. So this claim that I wrote shows that denseness can also be captured just by using open sets. So I will try to show you a proof of this. So say A is dense in X, and obviously here U should be non-empty. So for every non-empty open set, the intersection with A should be non-empty. So given a dense set, and let U be open, say that U intersection A is empty. So for the sake of contradiction, we assume that this intersection is empty. Then pick any element U, pick any element X from U. Then by the denseness of A, there exists a sequence such that AN converges to X. But from the equivalence of convergence using open sets, there should exist some natural number N such that a n belongs to U for every n greater than or equal to capital N. But this is a contradiction to the fact that the intersection is non-empty. Sorry, the intersection is empty. Therefore, what I can say is every non-empty open set must intersect with A. And the other direction is also, the other direction can also be proved easily, like this only. So that is a homework. Is it okay for everyone? Okay, so I will proceed. So another important notion is that of compact sets. So a subset. So compactness is in some sense a very similar thing to finite sets. So let me try to motivate this thing a bit.
Can you show the last slide once again?
Okay, fine.
Yeah, okay, fine.
Okay.
You can.
So let's come to the notion of compact sets. Uh, so so let's take, for sake of an example, R2. If we have some finitely many points in R2, and if say I have a collection of open sets which cover all of these points like this, which cover all of these points, then since these are finitely many points, I can find a finite subcover of the open sets which covers all those finitely many points. So what I'm trying to say is uh, what I'm trying to say is for finite sets in X, these are open sets, such that uh, let's call this set F. If F is contained inside union of some open sets, then this union could be arbitrarily large. It could be uh, countably, or in fact, it may be uncountably infinite. But since the underlying set is finite, there exists a finite. I can find finitely many of these open sets which also cover this F. Say this alpha is from some indexing set, then there exists a finite subset delta of this indexing set such that this also contains F. Is this clear to everyone?
Can you explain the last line that you wrote?
Uh, this line. So I'm trying to just motivate this compact set, like it is somewhat similar to finite things. So what I wanted to say is key. If F is a finite set and it is contained inside union of some open sets, then okay, I will try to explain this. So say F is F1 till Fn. So F1, all of these Fi's belongs to this union over union of these open balls. Therefore, F1 lies, this Fi lies in some open set U alpha I. Therefore, F1 till Fn is a subset of union of U alpha I from 1 to N. Is it clear now? Like I can, for every open cover of this F, I can pick finitely many of those open sets, which also covers the given finite set. Is it okay? So this is what this line meant. Is it clear now?
Yes.
Okay. And so for finite sets, this is clear. And one very important property that finite sets have is, if I for finite sets, if I take any map F, or if I take any map, say phi from F to real numbers, then this will attain minimum and maximum because there are only finitely many points. Say F1 goes to some real number R1 and Fn goes to real number Rn. So minimum and maximum of the image of this function is attained by this function. Minimum and maximum is attained. So this is a very easy property to see which finite sets follow. So compact sets are in some sense trying to mimic these properties of finite sets. So a compact set A, in which is a subset of X, it is called compact if for any open cover U alpha, what that means is that means A is contained inside union of these open sets. Say alpha belongs to this. Then I can find finitely many of these open sets which cover A. I can find finitely many. So I can find a finite set, finite subset of this indexing set, so that A lies inside union of, sorry. Okay. So is the definition clear to everyone? Is the definition of compact sets clear to everyone?
Yes, sir.
Okay. So it turns out that the properties that the nice properties that finite sets follow. So assuming this definition, we can also arrive at these properties. So compact sets are in some sense a very nice extension of finite sets in metric spaces. Okay. So because they follow some very nice properties of finite sets. So to give some examples and some non-examples, examples. So open 0, 1 in R is not compact. Is not compact. Why? Because consider the open cover that I'm giving you, 0, 1 by n, for say Oh, no, this will not work.
What is the subset here in the example?
This thing.
So like what the example? What is not compact?
So this open interval 0, comma 1. This subset of real line is not compact. This is what I'm trying to show over here.
The comma is as big as the one.
Oh, I'm really sorry for that. Okay. So this open interval 0, comma 1 is not compact. So
I think it should be 1 by n comma 1.
1 by n. Oh, yeah. I'm really sorry. 1 by n comma 1. True. So this collection of open sets, all of these are open sets, and their union contains this open interval. But no finite subset of this set can cover the entire open interval, because the maximum n that the finite subset of these sets have, beyond that we can't reach. So say like if from k equal to say some 1 to whatever, some alpha, if this contains, if this contains 0 comma 1, then take the max of n k 1 over that, and we can find a number between these 2 points, say whatever, say theta. So this theta will not, this does not belongs to this union 1 by nk. So therefore no finite subset of this cover contains the open interval 0 comma 1. And I think you might have studied Hein-Borel theorem in your real analysis 1 course. So that actually characterizes open sets in real numbers. Sorry, that characterizes compact sets in real numbers. Oh, sorry, I forgot the definition. I forgot the spelling. So some theorem which says that compact sets in R are exactly the closed and bounded subsets of it. Okay. So I didn't define closed sets yet. So let's talk about that also. Closed sets. Huh. Yeah. Okay, so I will just define closed sets and I will stop. Okay, so closed sets are given a metric space X, a subset of it is called closed.
Sir, can you show the theorem once again?
So this is the theorem.
Okay, thank you.
If it is complement of some open set, if it is complement of open set. So the main motive of this lecture is to show you that open sets can capture very important notions like convergence, continuity, like one of the most important thing that we do in real analysis, continuity, denseness, compactness, closed sets. So these are the things that I wanted to show you. In the next lecture, what we will do is we will try to generalize all these things, and so that we can study the consequences of open sets on its own without using notion of distances and all. So that's all that I wanted to cover this lecture. If some of you have any question, you can ask now, else we will wrap.
Can you send this PDF? Like,
Sure. Bikram, I will send this to you. And okay, fine. So does anybody have any question? Okay, fine. So I think we can. So it's done, I guess.